Okay then, this session will be about detailing and durability in accordance with the Eurocodes. The first thing we'll look at for this is durability requirements in the Eurocodes. We'll look at the environmental conditions and exposure classes, which are very similar to BS 8500. We'll then go on to cover detailing and lap length calculations, all in accordance with the Eurocodes. So starting off with durability. Basically, in the Eurocodes, it's the thickness of the cover is the most important consideration for the durability requirement. Crack width in itself doesn't actually affect durability that much, and that's one of the reasons why the covers have increased a lot over the last few years. It's basically just you get better durability from big covers than you do from calculating crack widths out. A good amount of cover also gives corrosion protection through reinforcement by providing a physical barrier and through the alkalinity of the concrete itself, which again helps prevent corrosion occurring within the reinforcement. There's some other important things to consider as well, and these include things like the concrete density. Obviously, the density of concrete is, the better your cover is going to be, and the more ability it's got to prevent contaminants getting into the reinforcement. Crack width does have some effect. You can't have really big crack widths occurring. So if you've got a 3 centimeter crack width, for instance, it is going to let contaminants in, and that's why you've got the 0.3 millimeter crack width limitation. And then you've also got the exposure conditions will also affect your durability. Obviously, if you're in a harsh environment, it's going to start breaking down the concrete, while if you sort of have a piece of concrete that's sitting inside, it won't affect the concrete nearly as much. So that has to be taken into account as well. Environmental conditions. This also comes in on. This also affects the exposure classes. And basically, on this slide, we've just outlined all the environmental conditions that the Eurocodes are concerned with. The top 4 that are given here, the chloride ingress, the carbonation, the frost attack, and the abrasion, are things that the Eurocode deals with directly, and those ones are included in the calculation that you do for your cover requirement in accordance with the Eurocode. The last 4, including the alkali-silica reactions, the sulfate attack, acid attack, and leaching, are not dealt with directly, but they're affected by the type of concrete mix that you choose. So if you've got those sorts of things affecting your concrete, you probably need to be careful with the type of concrete mix that you're selecting to make sure that you get one that suits the environment that you are putting it in. The cover thickness which is selected is dependent on the concrete exposure classes, and these exposure classes are covered in Table 4.1 of Eurocode 2 Part 1. And these classes will be quite familiar to you because they are also the ones that are given in BS 8500, and ones in A500 were actually based on the Eurocode ones. So there's a sort of overlap in that. And basically you've got the X0 exposure class, which is concrete inside. You've got XC, which is carbonation. XD, which is if you've got it in if you've got the icy salts and things like that on your structure or near your structure. XS is your seawater, if you've got something that's sort of sitting in seawater or sitting near seawater. And then you've got the other ones like XF, which is freeze thaw, and your XA, which is your chemical attack. And all these are given in Table 4.1, as I said. And this is just what the sort of table layout looks like in the Eurocode. Again, it's very similar to what's given in BS 8500. It uses pretty much the same definitions. The one thing to take note of here is that anything on these slides that are highlighted in bold, those will be bridge-specific requirements. Anything that's not in bold text applies to both bridges and buildings, but the bold ones are specific to bridges only. Basically, these tables are also laid out in terms of being the less severe class being on top, and the severity is gradually increasing as you go further down, with the absolutely worst exposure class being cyclic wetting and drying. And this then just continues on through looking at the various different exposure classes, and that includes XF and the XA ones as well. Now getting on to the deterioration mechanisms that are covered by the Eurocodes, and that's outlined on this slide here. Basically, for corrosion to occur in your reinforcement, you'll have to have access to both oxygen and sort of water. And if you've got if the reinforcement has both oxygen and water, the corrosion process will speed up and be the quickest. And that's why the worst possible exposure class you can have is the cyclic wetting and drying, because that basically exposes the reinforcement to both the oxygen and the water. If you bury a piece of concrete and it's just wet all the time, yes, it does have access to the water all the time, but there's no air, and therefore the corrosion process is a lot slower. And vice versa, if you've got a piece of concrete sitting in air but never getting wet, it doesn't have the access to the water. So, and that's why just the cyclic wetting and drying is the absolute worst you can get. And that's also why the XD3 and XC4 have the highest requirements for your cover. And it's just to deal with that cyclic wetting and drying process. So in accordance with the Eurocode, those are the basic things that we are looking at. But in the UK, we have adopted the BS 8500 approach, which basically essentially overrides what's in the Eurocode itself. It's one of those things that we're probably not allowed to do, but the Eurocode police haven't come and told us not to yet, and therefore we are still using BS 8500. But I wouldn't be surprised if in the next couple of years we'll probably get told to do it the same way as everybody else is doing it. So basically what we'll do here is I'll just go over both the 8500 requirements and the Eurocode requirements, so you know both methods. So when we do have to change over, you'll be aware how to do that as well. So basically, in the Eurocode, the things that are dependent on the things that depend on the concrete cover are environmental class, and as I said previously, that's exactly the same as for 8500. It also is dependent on the concrete strength. The higher your concrete strength, generally the denser the concrete is, and the better protection it provides. It will also depend on your design life, because if you've got a building that's subject to a 50-year design life, the cover requirements are going to be less onerous than if you've got a bridge that's subject to 120 years. You end up with slightly bigger cover in those cases. It's also dependent on the member geometry, and it's dependent on the member geometry because if you've got a slab, it's very easy to make sure that the bits of reinforcement that you've got go approximately where you want it to in that plane and approximately where you want it to in that plane. If you've got a beam with lots of links in, you've got to make sure that the links fit in exactly where you want them to, and you've got to get the bars in. And the probability of you achieving that is less than if you have a slab, just because you don't have the links involved. And because of that, if you do have a beam, you get slightly penalized on the cover side, and you end up with a slightly bigger cover than if you had a slab, just because of the ease of placement and reinforcement within that section. The final thing that it will depend on, in accordance with the Eurocodes, is quality control. And basically for this, the Eurocodes state that if you've got special quality control, you can also justify that you can reduce the cover slightly. However, it doesn't actually tell you what special quality control means. So generally speaking, I would recommend that you don't take any advantage of using special quality control if you're using this method, and just go with ignoring that. It's only really if you come on site, the contractors put all the reinforcement in at a reduced cover, and you then come in and you can justify using that clause, because then you know exactly where your reinforcement actually is, and you can sort of say, yes, it is exactly there, so we can justify reducing the cover requirements because of that. But if you're just doing a design in the design office, I would stay well clear of that. It's just not a very good idea to use unless you can justify the special quality control, which, as I said, hasn't been defined. And those are the things that are used in the Eurocode 2 method. As I said, BS 8500 does supersede this and uses a slightly different method. But it does take into account similar sort of things, but in a slightly different way. Okay, so the first thing here we'll do is go through exactly what you would do using the Eurocode method. And once I've gone through the Eurocode method, we'll just look at the BS 8500 method as well, just to show what we're actually doing at the moment. So to calculate your concrete cover, you go to table 4.3 in the Eurocode, and you start off with a structural class of 4. You start off with this structural class of 4 because the Eurocode tells you that you start off with a structural class of 4. So starting off with that, then if you've got sort of a bridge, and you've got a service life of 100 years, you have to increase that structural class by 2. Dependent on the strength class that you've got, you can then potentially reduce the structural class that you have. You then go on to look at whether you've got a member slab geometry or not. If you do have a slab, then you can further reduce your structural class. And then you look at the special quality control, and if you do have special quality control, you can further reduce that structural class if you needed to. Once you then come up with a final number for your structural class, you then read off from there in table 4.4. So for whichever exposure condition that you have, or exposure class, you just then read off for the structural class to find out what your nominal cover is. So if you had a XE4 type of exposure class with a structural class of 5, you would then end up with a nominal cover of 35 millimeters. So it's fairly straightforward on that. However, if you're using the BS 8500 method, you have to use the various tables within BS 8500, tables A6, 7, 10, 11, 12, and 13, and you then use that to calculate what your nominal cover is. And this is done by using this table here. This is just an example of one of the tables in the BS 8500. It's table A5, and there, here you would just look up for whatever sort of exposure class that you have, and you then read off this diagram to figure out what your sort of minimum concrete type is, and the sort of cover that you would then need to use for that. And you then sort of go on to using that table there, which is just, well, this is the same table, it's just didn't fit on the same slide. And from that, once you then have the nominal cover given up the top of this slide there, then you then just go on and go back to the Eurocode equations, and which is this one here. This is the same for both 8500 method and the Eurocode method. It's the only thing that departs is the nominal cover calculation.
Is nominal cover to 8500 the minimum cover in Eurocode?
Essentially, yes. It starts getting awfully complicated. It's one of those areas I don't particularly like 8500. It just confuses things. Using the Eurocode method is a lot easier. It really is. And it sort of fits together with all the rest of the Eurocode requirements as well, so it's quite clear where which number you're applying where. So anyway, once you've found out what your minimum cover is, you then have all these various other parameters that you add on to calculate what your actual C-min is. And you basically you also have this C-min, durability, which is our minimum cover for the durability, which allows for sort of additional national parameters. So if you have any sort of additional safety elements, if you want to reduce the minimum cover for using stainless steel, or if you want to use sort of any epoxy coatings or something like that to provide extra protection. It also sort of allows you in there to take benefit of that. In the Eurocode, all those are recommended to be 0, which is sort of probably fair enough. And it's probably best to use them as 0 unless you can justify it using some other sorts of means. As you can see from that equation, you also have you can never get a value less than 10 millimeter cover. Realistically, if you're doing a bridge design, you are never going to get anything even close to 10 millimeter cover. That's only really for buildings design. Covers for bridges are usually big. It's usually so at least 30, 40 mil, even for the sort of smallest cover element. So once you've got your nominal cover, you then also add on this delta C dev, which is recommended to be 10 millimeters for in situ cover. Where you have tighter quality control, you can justify that delta C dev can be decreased. So if you've got a precast member, and precast fabricator can justify that they can achieve smaller tolerances in the fixing of the reinforcement, then you can sort of reduce that. But I'd be very suspicious of anybody who said that they can have a fixing tolerance of 0 millimeters. I'd still sort of go with about 5 millimeters, even for the precast members. So the next thing we're going to do is go through an example for this. Again, we'll just go through both the A500 method and the Eurocode method. They actually come out with the same answer, which is quite nice, but at least for this example. We haven't done an extensive comparison between them, but they do seem to be indicating approximately the same sort of cover, so that's quite good, if nothing else. So basically here we're just going to look at a sort of simple slab. It's 250 mil thick. It's exposure class XD1, and it's got a design life of 100 years with a C35/45 grade concrete. So the first thing we do, looking at the Eurocode method, is to start off with a structural class of 4, because as I said previously, that's what the Eurocode tells you that you start off with. And for the XD1 class, we first of all look at the service life requirement. We've got a bridge, it said, and we've got our service life of 100 years. Therefore, we increase the structural class by 2, which means we've now got a structural class of 6. We can then look at the strength class. We've got a C35/45 concrete, which is not less than C40/50, so we cannot apply a reduction to the structural class. Next thing we look at is the member geometry. If you've got a slab-like geometry, you can further reduce the structural class, which in this case we've got a slab, so it does have a slab-like geometry. So that means that we've got a structural class of 5. And then you've got the special quality control. And as I said, generally speaking, we want to steer well clear of that, so we don't apply that at all. So that leaves us with a structural class of 5. So then we've got the structural class of 5 for the XD1 class. We just read off this table, and we come up with a cover of 40 mil, which is the C-min, durability. Now going to the 8500 method and doing exactly the same calculation. Here, looking up for the XD1 class, the C35/40 concrete, reading up the table, we come up with a requirement of 40 plus delta C. So that's again just showing that we have the same 40 millimeter cover requirement as we had to the Eurocode rules. And from there we then just add on this delta C dev, which is 10 millimeters, because we've a normal reinforced concrete member cast on in situ. And that means that our C nominal for the cover is 50 millimeters. So.
Are you going to cover what we detail that on the drawings?
What?
Because there's a guidance now about target cover.
Mm-hmm.
Are you covering that?
Not really, no. That's all I was going to say about cover.
Details of the tiny cover in between the C1 and the C.
It's not really the same now. It's that if you look at the EN 13670, which is the execution standard for the concrete, it'll then give you the various requirements in there of where you detail it and what the tolerances are. EN 13670.
Is it the same as these delta C or Eurocode?
It isn't really, no. It's BS5400 and the Eurocodes are slightly different.
The 84500, there is a delta C term.
Yeah, that delta C is the same.
That's
the 10 millimeters, yeah.
So remember, it's different.
This slide here is the same for both methods. That's why we haven't shown two different versions. It's
yeah, but it's amended by the EN to be 10 for 250 slab.
yeah. So
Sorry. Also, in 8500, it has the different cement types. Is that not taken into account in
no,
orders?
the cement types are not taken into account in the Eurocode really. It's the Eurocode is a lot more basic in the way it approaches things.
I think we should still be taking that into account when we're using the sort of combination of the two now, should we? Or?
You're not really supposed to be using the combination of the two. At the moment, the Eurocode says that you shall use basically what we've got is you got the Eurocode, and the structural class thing that I was talking about is a nationally determined parameter. And what the UK National Annex does is, instead of giving a sort of number for the structural class, it tells you use BS 8500 to calculate what your cover is, and then that number then feeds in to the rest of your calculations. And that's where it probably isn't quite right the way we've done it, because you're not supposed to have a whole bunch of tables in as a nationally determined parameter, which is why I think that in a couple of years' time we'll have to change the national annex to be compliant with the Eurocode method we've gone through here. But at the moment, it's the 8500 method that applies if you're doing any designs within the UK.
Okay. And then we would still obviously have to...
And then you have to use all the, then you have to take into account the concrete sort of composition and everything else.
And to check the practice, we use the 85400 cover with practice.
Yeah. You use but
If it's like 75 millimeter cover, which we usually get.
But you'll end up with 75 millimeter cover probably to the Eurocode as well for that sort of situation.
Based on Eurocode, but based on the S5400, we usually use that 35 millimeter 5400 and check that practice at that 35 millimeter at 800 reinforcement and not 75.
Well, you'll check the cover to whatever it comes out of BS 8500.
Even with that deviation, it could be fixed at 40 mil, couldn't it?
Well, you'll include the sort of deviation to 10 millimeters.
But what if it's fixed at 40 mil and you're doing durability counts to 40 mil, to 50 mil, and it could be 40?
Yeah, but the calculations would be more onerous if you've got a 50 mil cover.
Right.
So it's basically, you have to keep in mind you are doing this at the design stage. You won't know if they're going to fix it outside that sort of requirement, so you'll be doing it for whatever you design it for. You can't really do anything else than that. Next thing we're going to look at is the detailing rules that are given in the Eurocode. The detailing rules are given in clause 8 of the Eurocode, and the detailing rules will depend on things like the concrete type and strength, surface characteristics of bars and what sort of deformations they have on the bars, the shape of the bars, and that's basically, is it a straight bar or have you got bends in it. It will also depend on the concrete cover compared to the sort of bar size that you're dealing with. If you've got any welded transverse bars, If you've got any additional confinement due to links or additional transverse bars, and if you've got any additional confinement due to transverse pressure. What it means with that is just you have something like a bearing underneath that's providing pressure underneath local to where your reinforcement is, and it allows you to take advantage of that if you want to. The detailing rules in the Eurocode do not fully cover things like coated bars. So if you had a sort of coating on your bar, the coating may affect the bond characteristics of the bar, and therefore it's not really properly taken into account by the sort of detailing rules that are given, and you have to do some sort of further work to quantify what the sort of bond actually is. It also doesn't fully cover things like seismic loading, at least not in Eurocode 2 Part 1 and Part 2. There is some additional requirements given in the sort of seismic design code, which I think is Eurocode Part 7 or 8 or one of that, something like that. And that's not 7 because it's 8. And that gives some additional detailing requirements. And basically that's just because if you've got a structure in a seismic zone, you need some additional ductility within that structure to design for the seismic effects. Generally speaking, the detailing rules that are given in Eurocode 2 do assume that the minimum cover requirements have been complied with. And that's particularly important for anchorages and lap lengths, where the strength could potentially be reduced if you aren't complying with the cover requirements. So do keep that in mind. You do have to make sure that you are complying with cover requirements, otherwise you're not complying with the detailing rules in here. There are also some practical rules for minimum spacing of reinforcement that are defined in Eurocode 2. And these rules are designed to ensure that the concrete can be placed and compacted and enable adequate bond strength to be developed along the length of the bar. There's also some absolute minimum spacings that are given. And the absolute minimum spacing is the greater of either the bar diameter or the aggregate size plus 5 millimeters, or 20 millimeters, whichever one is the greatest. However, those minimum spacings should only be used in very local areas, because otherwise you'll end up with problems trying to get the concrete in and the concrete properly vibrated. I'm sure you've all had situations on site where you just end up with too much reinforcement and the concrete just doesn't fit. Those sort of practical rules you still have to observe. Those minimum spacing requirements are something that only put those in sort of very localized regions. Don't put them everywhere, because you're going to end up with other durability problems coming up, just because you're not going to be able to vibrate the concrete properly. There's also some requirements given for the minimum bend radii of the sort of section. And basically here, this section states that the mandrel diameter does not require specific checking for the concrete failure, providing that you comply with these 3 requirements. The first of this is that the anchorage of the bar does not require length more than 5 times the bar diameter beyond any length of the bend. Basically that just means that when the bar starts being bent, it's not fully stressed at that point. You also have to make sure that the plane of the bar bend is not positioned close to the concrete base, and that's just to prevent spalling from occurring. And you also need to have a bar of at least the same diameter inside the bend. And finally, you have to make sure the mandrel diameter is at least equal to the recommended values that are given in Table 8.1, which I'll show you on the next slide. If you can't comply with one of those requirements, you can calculate the required mandrel diameter from that equation given down the bottom there, which is just dependent on the bar diameter, which is phi, FBT, which is the tensile force from the ultimate loads within the bar itself. You've got AB, which is half the center-to-center distance between the bars, and finally the FCD, which is just the concrete design compressive strength. If you look at the Eurocodes, the compressive strength that you're allowed to use cannot exceed C55/67 type concrete if you do exceed that, you'll have to sort of reduce the value for that equation. And this is the equation, the table I was talking about previously, the minimum mandrel diameter table. If you've got a sort of bar diameter of less than or equal to 16 millimeters, your minimum bar mandrel diameter is 4 times the bar diameter. And if you've got a bigger bar, sort of a 20 or above really, you then have to make sure the minimum mandrel diameter is at least 7 times the bar diameter. So again, those are nationally determined parameters, but we've just adopted the recommended values in the UK. And then next we're going to go on and looking at the anchorage of longitudinal reinforcement. Basically, the reinforcement needs to be adequately anchored to ensure that bond stresses are transmitted to the concrete without any longitudinal cracking or spalling occurring within the section. And the transfer of these stresses is mainly by mechanical locking of the reinforcement ribs with the surrounding concrete. And that will depend on the shape of the bar, cover, the transverse reinforcement, and any confinement from transverse pressure. This figure here then just shows you the sort of the different anchorage methods that are given in the Eurocodes, other than a straight bar. A straight bar is also a permitted anchorage method, obviously enough. These ones here are the ones that are just given in the Eurocode. You are allowed to use other anchorage methods if you can justify them. You can do that through sort of testing of some sort. The Eurocode is actually very flexible to allow you to try different methods of doing things, and it will give you a couple of recommendations of this is a way of complying with the requirements. But then if you can justify it by some other means, such as testing, you can then also use that method. So it's quite good really from that point of view. Generally speaking, the anchorage failures will take one of 3 different forms, and those forms are illustrated on this slide here. The first of this is the side split failure, which is the one shown on the left-hand side over here. And basically the side split failure will occur if your cover is less than half the clear spacing between your bars. So basically that C dimension there is bigger than sort of half of A divided by 2 basically. And in this sort of scenario, you basically end up with a crack forming between the bars, as shown in this diagram here, and then the cover just sort of falling off and exposing the bar to corrosion. The second method of failure will occur if you've got the cover being less than the sort of A divided by 2. And in this sort of situation, you'll end up with some cracks forming vertically from the bar down to the face of the concrete. And if the sort of A divided by 2 is just slightly bigger than C, you'll end up with, after those vertical cracks start forming, you'll end up with horizontal cracks forming and then the concrete spalling off. If you've got a situation where A divided by 2 is a lot greater than what the cover is, then you'll instead end up with these vertical cracks forming. But instead of the horizontal crack sort of forming, you'll end up with sort of cracks forming at 45 degrees away from the bar, and that piece of concrete falling off locally, and again exposing the reinforcement. And basically, those sorts of failures can be controlled by providing things like transverse reinforcement or transverse pressure just to keep the cover onto the section. And the Eurocodes do make an allowance for taking that into account, and that's taken into account in your anchorage calculations and your lap length calculations as well. So to actually calculate your anchorage length, the first thing that you have to do is calculate your ultimate bond strength, or ultimate bond stress rather. And you do that by using the equation illustrated above there, where you've got the bond strength is equal to 2.25 N1 times N2 times FCTD. N1 just relates to the quality of the bond condition and the position of the bar during the concrete. And basically, if you've got a bar sitting at the bottom, you then have an N1 factor of 1, and if you've got a bar sitting in the top, you've got an N1 factor of 0.7. And that's basically just to allow for the fact that the concrete in the bottom of the slab is probably better compacted than the concrete in the top of the same slab. Then 2 factor just relates to the bar size. So if you've got a big bar that's bigger than sort of a 32 mil bar or bigger, you end up making a reduction to that. If you've got the smaller bars, then it's just N1 is just N2 rather is just equal to 1. And FCTD is just the concrete design strength, and again that's just taken from table 3.1 in the code. So once you've calculated your ultimate bond stress, you then use that to calculate your basic anchorage length. And the basic anchorage length is also shown on this slide here, and is just dependent on the bar diameter, the stress in the bar, and ultimate bond strength. And that basically allows you to take into account if you've got a bar that's not fully stressed. And again, that's one thing that you're probably best off not really doing if you're doing a new design. You're better off just assuming that the bar is fully stressed. But it's another sort of get-out clause if things start getting wrong and you end up with smaller anchorage lengths than you expected. So once you've got your basic anchorage length, we then have a whole bunch of alpha factors that we use to modify what this anchorage length is. And these alpha factors are numbered alpha 1 through to alpha 5 and are dependent on various different factors. And I think probably the best way of sort of illustrating what they are is on the next couple of slides, which are extracts from the codes. The only other thing I'm going to say to this slide is that you've also got some minimum anchorage length requirements depending on whether your bar is in tension or compression. And again, those are just shown on this slide here. Generally, to comply with those, to actually have the minimum anchorage length applying, you will have had to do a calculation where your stress in the bar is less than the sort of yield strength of the bar, so the bar isn't fully stressed. So as I said, we'll go on and look at the different alpha factors that you use to modify your basic bond strength. First of all, we've got the alpha 1 factor, and this is dependent on the shape of the bar. So if you've got a straight bar, alpha 1 is equal to 1. If you've got a sort of bent bar, or basically here it says other than straight, which basically means bent, you can then make a reduction to the alpha 1 factor. If you've got compression, you're not allowed to modify it. But if you've got tension, you can modify it as sort of stated on that slide there. For alpha 2, that's dependent on the concrete cover that you've got, and will also depend on if you've got a straight or not straight bar. And again, it also depends on if you've got a compression or tension within your section. Compression, you don't get to make a reduction, but tension, you can potentially do so using those equations given there. Alpha 3 will be dependent on if you've got any confinement by transverse reinforcement that hasn't been welded to the main bar. That basically just means links or something like that containing the bar. And again, this is dependent on whether it's in tension or compression. Compression, you don't get to make a reduction, but with tension you do. And alpha 4 will depend on confinement by welded transverse reinforcement. And that's basically just if you have a piece of transverse reinforcement that's been welded to the longitudinal bars and thus restrains it. And again, you've got the reduction factors given that shown there. The final thing is the alpha 5 factor, which is just dependent on the transverse pressure. And as I said earlier, an example of that would be if you've got a bearing underneath a beam, and that bearing will provide sort of a restraint onto the sort of bar, and you can take that into account in your sort of anchorage length calculation. So that is what you can do. Generally speaking, I would not recommend that anybody actually uses any of these reduction factors. And the reason for that is that if you've got a typical structure, you then do a sort of calculation on all the different anchorage lengths you have. And you probably don't want lots of different anchorage lengths in different parts of the structure, because it's pretty much guaranteed that if you have sort of 3 different types of anchorage lengths for a B20 bar, you'll end up with the contractor picking one and going with that everywhere, and they will mess it up. So it's one of those things. You're better off just using the same anchorage length or lap length throughout the entire structure, and using these clauses as sort of justification when things aren't done as they should be on the site. It might be also an area that if you have a discussion with the contractor, they might want you to start applying these, and then you'll have to make sure that they are actually applying it on site, because it is a very big potential error for fixing reinforcement on site. It's very easy to get it wrong if you've got lots of different anchorage lengths and lap lengths throughout the structure. It's the guys fixing the reinforcement are just going to get it wrong, basically. Lap length. Basically, the types of failure that you get with laps are pretty much the same as the ones that you will get for anchorage failures. It's just instead of a round failure sort of surface, you'll end up with an oval-shaped one to take into account both bars. But apart from that, the sort of failure surfaces that you tend to get are exactly the same. Generally speaking, some sort of guidance that you should be sort of using is making sure that you sort of make sure that you don't locate laps within areas of high stress if you can avoid it. You should also make sure that you stagger laps. Sometimes it isn't possible to stagger laps very well, particularly if you're sort of coming in from a pile into a sort of footing connection or something like that. In those situations, it is quite difficult to get your laps staggered. But generally speaking, as now, if possible to stagger laps, you should stagger them. So it's a general practice behind sort of laps is not really that different. And same as before, you're not locating laps in areas where you've got really high stresses. Again, if you've got a pile to sort of abutment connection, that might be difficult because the connection usually is in a very high sort of moment zone, so it's hard to avoid. But if you've got a deck, you probably put the lap somewhere sort of at the point of contraflexion rather than at the biggest bending moment. So it's pretty much just stating good practice on that slide. This slide here just gives you the requirements given for the laps, and basically it just tells you that you have to make sure that the clear transverse distance between two lap bars isn't greater than 4 times the bar diameter or 50 millimeters. And that's just illustrated by this middle sort of requirement in there. You can exceed that, but if you do exceed that spacing, then you have to make the laps longer, essentially. And that's just to take into account the sort of compression struts transferring the load between one bar and another bar. So if you exceed that distance, you have to sort of increase the lap length by the same sort of amount. You also have to make sure that the clear distance between adjacent bars and adjacent laps isn't less than 2 times the bar diameter, or 20 millimeters. Basically, that's just saying don't put your bars too close to each other. And finally, you have to make sure that longitudinal distance between 2 adjacent laps isn't less than 0.3 times the L0. And that's basically just sort of saying you should have staggered laps, and that's why it considers to be a staggered lap. So the lap length calculation is very, very similar to the one that we had for the anchorage length. If you look at that equation, you've got the same sort of alpha factors as you had for the anchorage length calculation. The only difference is that you've got an alpha 6 factor here, which takes into account the staggering, and you don't have the alpha 4 factor that you had in your anchorage length calculation. Apart from that, all other alpha factors are exactly the same as the anchorage length calculation, and they're calculated in exactly the same way as well. For the alpha 6 factor, it is slightly different from the other alpha factors in the fact that alpha 6 is almost always bigger than 1, so it never acts as a reduction factor. And as I said, it's dependent on how well staggered you have your section. And again, the staggering rules in the Eurocode are actually sort of slightly different from the Type 400 ones. To have a fully staggered lap in the Eurocode, you actually have to quadruply stagger them. And I'll show you what that looks like on the next slide. If you do the normal thing that we do in the UK with sort of every second lap being staggered, then you actually get this alpha 6 value will be 1.4, and that's considered to be a 50% staggering. And basically, for this, you just to consider how well staggered it is. You just so take your sort of top bar here, and then at the center, extend 0.65 times L naught on either side of the center of that lap, and then look at the bars adjacent to it and sort of see if those are staggered. So in this sort of situation, the center line of that one is outside, the center line of that one is outside, but the center line of that one is inside. So 2 out of the 4 bars are sort of staggered, and therefore it's 50%. So as I said, now I was going to show you a picture of a fully staggered lap in accordance with the Eurocodes, and that's a 25% staggering in accordance with the Eurocodes, and that's the one that's shown on the bottom right-hand corner here. That's a fully staggered lap in accordance with the Eurocode. Anything less than that, and you'll end up with an alpha 6 value bigger than 1. So it's basically a bit of a change to what we're used to. Other things to consider is additional transverse reinforcement that's required within the lap zone, and that's just shown in that picture on the bottom left-hand side there. And basically, if you've got lap bars that are bigger than 20 millimeters, you do have to provide some additional transverse reinforcement. And this additional transverse reinforcement has to be the sum of the area of one lap bar.
How big is the 25 staggering being detailed out in the drawing?
What?
How could this type of staggering to be detailed out in the drawing?
I'm not entirely sure how you'd detail it. It's
I mean, CAD's not a secret.
Yeah.
And then there's other software as well, advanced concrete as well, that CAD sections use. It does have provision for laps to Eurocode, but I don't know to what extent it kind of does all this, because it's complicated, really.
I don't really know how it would do it. Generally speaking, I think you're going to have problems fitting a 25% staggering into most bridges as well. That's quite practical if you've got lots of sort of 40, 50 meter spans, but practically most of the structures that we deal with are quite a lot shorter.
You're going to get the 50% stagger, the same as we always have, and it's 1.4 times the Anchorage.
Yeah, you'll end up with that. Yeah.
Yeah, what we're saying is you can't get in.
Yeah, we know we have to run it.
Yeah, well, you'll probably end up with a situation where you will end up with a 50% staggering and multiplying it by the 1.4 factor, and only using the 25% staggering in sort of probably fairly rare circumstances, because it's not that practical really, unless you've got a fairly big structure. So, but again, it's something you need to be aware of so you can take it into account, because if you're not complying with the detailing rules, you're essentially not complying with the rest of the Eurocode, because everything sort of fits together.